In 1953, the big three automakers were effectively selling a lie. They produced massive V8 engines promising high performance, yet intentionally suffocated them with conservative engineering designed solely for silence and warranty safety. But in a small Florida machine shop, a mechanic named Harvey Crane uncovered the truth. He discovered a geometric loophole, a specific, aggressive way to grind a camshaft that Detroit's executives were terrified to implement. To the corporations, this innovation was a financial liability. To the aftermarket, it was the key to unlocking hidden horsepower. This is the story of the mathematical secret that sparked a decades-long Cold War between the factory and the street. The mechanic who beat Detroit. Imagine standing on the corner of Woodward Avenue in 1955. A brand new Chevrolet Bel Air rolls up to the stoplight. It is a masterpiece of post-war optimism, dripping in chrome and powered by the new revolutionary small block V8. As it sits there, the engine is barely audible. The idle is glass smooth. The driver rests a hand on the steering wheel, feeling absolutely zero vibration. To the average consumer, this was the pinnacle of automotive luxury and engineering excellence. Now, cut to a humid Saturday night at a local drag strip in South Florida. The same make of car pulls up to the line, but this one sounds completely different. It isn't purring, it is chopping. The idle is rough, rhythmic, and aggressive. The exhaust note is a violent staccato that shakes the ground. When the light turns green, this car doesn't just accelerate, it explodes off the line, pulling engine speeds that would send the factory version to an early grave. The difference between these two machines wasn't the pistons, the crankshaft, or the displacement. The difference was a single machined steel stick buried deep inside the engine block. One was designed by a committee of corporate engineers terrified of warranty claims. The other was ground by a mechanic in a Florida machine shop who had discovered a geometric secret that Detroit refused to touch. This is the story of Harvey Crane Jr. and the camshaft trick that unlocked the true potential of the American V8. It was a technical innovation so aggressive that major manufacturers actively engineered against it, creating a decades-long Cold War between the reliability-obsessed boardroom and the horsepower-obsessed aftermarket. To understand why a simple piece of steel caused such a divide, we have to look at the landscape of the 1950s. This era is often remembered as the golden age of American manufacturing. The economy was booming, gas was cheap, and the public had an insatiable appetite for the automobile. But beneath the tail fins and the two-tone paint, a massive technological shift was occurring. The industry was moving away from the old flathead engines and embracing the high-compression overhead valve V8. These new engines, like the Oldsmobile Rocket and the Chevy Small Block, were marvels of potential. They breathed better and revved higher than anything that had come before. But there was a catch. The big three, General Motors, Ford, and Chrysler, were not in the business of building race cars. They were in the business of mass production. Their primary goal was to sell cars to the widest possible demographic, from the teenager to the grandmother. This reality dictated a philosophy of extreme conservatism in engineering. The most feared department in any automotive company wasn't the racing division, it was the warranty department. Every component had to pass strict durability tests. An engine needed to start in freezing temperatures, idle silently in traffic for hours, and last for years with minimal maintenance. The camshaft is effectively the brain of the engine. It tells the valves when to open, how far to open, and when to close to let air in and exhaust out. In the 1950s, factory camshafts were designed with a singular focus: comfort. They used symmetrical profiles, meaning the valve opened and closed at the same gentle rate. They kept the valves open for a short duration to ensure high vacuum at idle, which made the brakes work better and the engine run smoothly. To an engineer looking for power, these factory camshafts were effectively restrictor plates. They deliberately suffocated the engine's breathing to ensure it was polite enough for the general public. Detroit knew these engines could make more power. The physics weren't a mystery to them. But unlocking that power meant sacrificing that silky smooth idle and risking the longevity of the valve train. They viewed aggressive camshafts as a liability, a source of noise, vibration, and harshness that would drive customers away and drive warranty costs up. Into this world of regulated politeness stepped Harvey Crane Jr. He was not a corporate executive. He was a hot rodder and a machinist, operating out of a corner of his father's industrial shop in Hallandale, Florida. In 1953, while Detroit was busy trying to make cars quieter, Crane was trying to make his personal flathead Ford V8 and his motorcycle faster than anything else on the street. Crane looked at the internal combustion engine differently. He didn't care about a 3-year warranty or whether the car idled smoothly in the church parking lot. He cared about volumetric efficiency, the science of stuffing as much air and fuel into a cylinder as physically possible. He began by regrinding stock camshafts, reshaping the lobes to change how the valves operated. But unlike the grease monkey stereotypes of the era, Crane approached this with the rigor of a scientist. He realized that the factory approach to cam design was fundamentally flawed for high performance. The engine didn't want symmetry. It didn't want politeness. It wanted a specific aggressive geometry that could compensate for the restrictive exhaust ports found on early V8 heads. Crane founded the Crane Engineering Company in 1953 with a singular focus: to professionalize the black art of camshaft design. He moved the industry away from intuition and toward calculation. He saw the engine as an air pump that was being strangled by its own components. While the automotive giants were content with leaving horsepower on the table in the name of comfort, Crane saw a vacuum in the market. He realized that there was a growing subculture of racers and enthusiasts who didn't care about a rough idle or a little extra noise. They just wanted to win. This divergence set the stage for a revolution. Harvey Crane was about to introduce a design philosophy that would make the conservative engineers in Detroit look obsolete. He was developing a way to manipulate the valve events so precisely that he could trick the engine into making horsepower that the factory deemed impossible. Geometry behind the speed. Harvey Crane was operating in a different reality than the engineers in Detroit. While the automakers were treating engine building as a manufacturing challenge, focusing on assembly line speed and unit cost, Crane viewed it as a physics problem. Working out of the corner of his father's machine shop in Hallandale, Florida, he realized that the camshaft was not merely a mechanical stick spinning in the block. It was the engine's brain. It contained the programming that dictated every breath the engine took. If you could rewrite that program, you could fundamentally change the engine's personality without altering a single piston or connecting rod. The accepted wisdom of the 1950s dictated that camshafts should be symmetrical and uniform. In a standard single-pattern cam, the intake lobe and the exhaust lobe were identical twins. They had the same lift and the same duration. If the intake valve stayed open for a specific amount of time, the exhaust valve did the exact same. This symmetry made machining easy and the math simple, but Crane realized that an engine is not a symmetrical device. The physics of pulling a cold, dense air-fuel mixture into a cylinder are radically different from the physics of pushing hot, expanding gas out of it. This discrepancy was magnified by the design of early overhead valve cylinder heads. To save money and fit the engine into tight engine bays, Detroit engineers often compromised the exhaust ports. They were twisted, pinched, and restrictive. The engine could inhale reasonably well, but it struggled to exhale. In the racing world, this phenomenon was known as the big cork. As RPM increased, the engine would choke on its own exhaust fumes because the spent gas couldn't exit the cylinder fast enough before the intake valve opened again. Crane's first major deviation from the norm was the dual or split pattern camshaft. It was a simple yet profound realization. If the exhaust port is a bottleneck, the valve needs to stay open longer to compensate. Crane began grinding camshafts where the exhaust lobes were physically larger, fatter, than the intake lobes. Think of it in terms of crowd control at a theater. If the entrance door is wide, but the exit door is narrow, you cannot have both doors open for the same amount of time if you want to clear the room. You have to hold the exit door open longer to allow the crowd to squeeze through the restriction. By increasing the duration of the exhaust event, Crane used time to compensate for the lack of space. This allowed the cylinder to fully scavenge the exhaust gas, leaving a clean, empty vacuum ready to suck in a fresh charge of air and fuel. This dramatically increased volumetric efficiency, not by changing the cylinder head, but by changing the schedule of events. However, the split pattern was only half the equation. The true secret and the innovation that terrified the warranty departments was the asymmetrical lobe profile. Standard factory camshafts used a symmetrical profile. If you looked at the cam lobe, the ramp that pushed the valve open looked exactly like the ramp that let the valve close. It was a mirror image. This was great for smooth operation, but terrible for power. A symmetrical cam opens the valve lazily and closes it lazily. In a high-performance engine, you want the valve to snap open instantly to get maximum airflow as soon as possible. Crane looked at the geometry and decided to separate the opening event from the closing event. He designed lobes that were aggressive and asymmetrical. The opening ramp was steep, nearly vertical. It acted like a hammer, kicking the valve open with extreme velocity to reach maximum lift almost instantly. This flooded the cylinder with fuel and air much earlier in the cycle. But if you closed the valve that fast, you would destroy the engine. A valve slamming shut at that velocity would bounce off its seat, float the springs, or even snap the head off the valve. This was the trap that caught many amateur grinders. They made the cam too aggressive on both sides. Crane's genius was in the asymmetry. The front of the lobe was a cliff, but the back was a gentle slope. He engineered the cam to kick the door open violently, but then catch it and set it down softly. This slow closing ramp managed the kinetic energy of the valve train, ensuring the valve seated gently even at 6,000 revolutions per minute. This unique geometry allowed the engine to breathe like a race car on the intake stroke, but survive like a passenger car on the compression stroke. Implementing this geometry revealed the weakness of the surrounding components. The steep hammer-like opening ramps placed immense stress on the valve train. The standard stamped steel rocker arms used by the factory would flex, gall, or burn up under the friction. To make his camshafts viable, Crane had to invent the support system to run them. He introduced gold anodized roller-tip rocker arms with needle-bearing fulcrums. These components replaced sliding friction with rolling motion, allowing the valve train to survive the violent acceleration his camshafts demanded. The economics of risk. When we say that Detroit hated Harvey Crane's camshafts, we need to clarify what that actually means. It creates a dramatic image of executives in a boardroom flipping tables because a mechanic in Florida outsmarted them. But the reality was far more pragmatic and, in many ways, more interesting. The animosity wasn't born out of jealousy or technical spite. It was born out of risk management. The automotive industry in the 1950s was engaged in a high-stakes balancing act, where the physics of horsepower were constantly at war with the economics of mass production. The engineers at GM, Ford, and Chrysler were not incompetent. They understood the same fluid dynamics and valve kinetics that Harvey Crane did. They knew that an aggressive asymmetrical camshaft would unlock massive amounts of power, but they also knew something Crane didn't have to worry about: the behavior of the average consumer and the financial devastation of a widespread warranty recall. To understand the mechanical root of this conflict, we have to look at the interface between the camshaft and the lifter. In the 1950s, the standard technology was the flat tappet. This is exactly what it sounds like: a flat-bottomed metal cylinder that rides directly on the spinning lobe of the camshaft. It is a friction-based system. The camshaft slides against the bottom of the lifter, spinning it to distribute wear. This system works perfectly fine when the cam profile is gentle. But Harvey Crane wasn't designing gentle profiles. Remember the quick opening ramp we discussed? The nearly vertical cliff that snapped the valve open to fill the cylinder? That geometry created a massive spike in what engineers call Hertzian contact stress. Hertzian stress refers to the localized pressure created when two curved surfaces come into contact under load. When a crane cam with a steep opening ramp slammed into a flat tappet, the contact point became a zone of extreme metallurgical violence. The lifter wasn't just sliding up a ramp, it was effectively being struck by a hammer thousands of times per minute. For a professional racer, this was an acceptable trade-off. A racer checks their valve lash constantly. They use high zinc oil. They expect to tear the engine down after a few weekends of competition. If a cam lobe gets wiped out, it is simply the cost of doing business in the pursuit of victory. But for a mass manufacturer, this scenario is a nightmare. Detroit builds engines for the doctor who never checks his oil, the family that drives cross-country in the summer heat, and the commuter who idles in traffic for hours. If GM had installed Crane's aggressive asymmetrical cams in a 1955 Bel Air, the increased contact stress would have led to rapid wear on the cam lobes. The metal would flake off, circulate through the oil system, and destroy the bearings. Instead of an engine lasting 100,000 miles, it might fail in 15,000. In the mid-20th century, the American automotive industry was the largest industrial sector in the world. A failure rate of even 1% could mean tens of thousands of warranty claims, millions of dollars in losses, and irreparable damage to a brand's reputation. The hatred for Crane's design was actually a rational rejection of a component that was statistically guaranteed to fail under normal consumer neglect. Beyond the threat of mechanical destruction, there was the issue of NVH, noise, vibration, and harshness. The 1950s consumer defined luxury by isolation. They wanted cars that floated down the highway and idled so smoothly you had to look at the dashboard to see if the engine was running. This was the era of the Dynaflow transmission and silent flight rides. Crane's camshafts were the antithesis of this philosophy. By extending the duration of the valve events and increasing the overlap, the moment when both intake and exhaust valves are open simultaneously, Crane ruined the engine's idle quality. A high-performance cam lowers the manifold vacuum at low RPMs. This creates that choppy, rhythmic lope that hot rodders love. But to a Cadillac engineer, that sound is a failure. It represents inefficiency and roughness. Furthermore, low vacuum creates functional problems for a passenger car. Power brakes and vacuum-operated accessories rely on steady engine vacuum to function. A car with a Crane cam might require the driver to stand on the brake pedal with both feet just to stop at a red light because the vacuum booster isn't getting enough pressure. The dashboard would shake, the exhaust would smell of unburnt fuel. To Detroit, this wasn't performance. It was a defective product that no suburban family would buy. Then there was the sheer cost of manufacturing. Harvey Crane could afford to be meticulous because he was producing small batches of premium products. To make his aggressive flat-tappet cams survive, he had to use specific metallurgy, precise heat-treating processes like nitriding or parkerizing, and mirror-like surface finishes. Scaling these processes up to production levels of millions of units per year is incredibly expensive. Every extra minute a part spends in a heat treatment oven and every extra pass on a grinding machine adds to the unit cost. If Detroit adopted Crane's geometry, they would have had to upgrade the hardness of every camshaft and every lifter in their inventory. They would have to tighten their tolerances and slow down their assembly lines. In the high-volume business of Detroit, saving 50 cents on a casting could result in millions of dollars of profit at the end of the year. Spending $5 extra per camshaft to achieve a horsepower number that most customers would never use was financial suicide. The friction between Harvey Crane and the Big Three was ultimately philosophical. Detroit was playing a game of averages. They designed for the mean, the average driver, the average oil quality, the average commute. Their goal was reliability and predictability. Harvey Crane was playing a game of peaks. He designed for the maximum possible output at the absolute limit of mechanical adhesion. This is why the secret trick remained a secret from the factory floor for so long. It wasn't that Detroit didn't understand the trick. It was that they couldn't afford to use it. They looked at the physics of the asymmetrical lobe and saw a warranty claim waiting to happen. Crane looked at the same physics and saw a trophy. The hatred was simply the sound of two completely different industries looking at the same piece of steel and seeing two completely different purposes. The industry finally catches up. The debate between Detroit's conservative engineering and Harvey Crane's radical geometry was ultimately settled not in a boardroom, but on the quarter mile. In the world of automotive performance, there is no greater validator than the scoreboard. While General Motors and Ford were fretting over warranty claims and idle quality, Crane Cams was systematically dismantling the competition on the racetrack. Throughout the 1950s and 60s, the secret trick of the asymmetrical camshaft ceased to be a theory and became a prerequisite for winning. If you were running a small block Chevy at a Saturday night oval track or piloting a supercharged funny car down a drag strip, you weren't running a stock factory camshaft. You were running a Crane. The aggressive opening ramps that terrified factory engineers were propelling cars to records that stock components couldn't physically achieve. The sheer dominance of Crane-equipped engines proved that the science was sound. The engine didn't explode if you opened the valves fast. It only exploded if you didn't have the engineering prowess to control the valve train. This success forced a shift in the industry's perception. What was once considered a radical modification for the lunatic fringe began to look like the standard for performance. But Harvey Crane knew that intuition and manual grinding had a ceiling. To push the camshaft further, he had to leave the analog world behind. In 1965, Crane Cams introduced a development that widened the gap between the aftermarket and the OEMs even further, the CompuCam. This was the first time a computer was used to design camshaft profiles. Before this moment, cam grinding was a black art, often done by hand and eye, relying on the steady touch of a master craftsman. But a human hand, no matter how steady, cannot grind a mathematically perfect asymmetrical curve to within a 10,000th of an inch. By utilizing early mainframe computing, Crane could mathematically model the valve events. He could smooth out the acceleration curves and precisely calculate the jerk, the rate of change of acceleration, to ensure the lifter stayed in contact with the lobe. This allowed for even more aggressive profiles that remained stable at high RPM. While the giants of Detroit were still largely relying on traditional drafting and prototyping methods for their internal components, a small company in Florida was using the digital age to rewrite the laws of combustion. However, the final piece of the puzzle, the innovation that would eventually bridge the gap between Crane and Detroit, was the solution to the friction problem. The primary reason Detroit rejected aggressive cams was the wear on flat tappet lifters. Crane's answer was the roller lifter. Crane cams pioneered the mass production of roller tip rocker arms and mechanical roller lifters. By replacing the flat, sliding face of the lifter with a precision wheel that rolled over the camshaft lobe, the friction equation changed entirely. The hammer effect of the aggressive opening ramp was no longer a durability crisis because the rolling wheel could handle vastly higher loads than a sliding metal surface. The roller lifter eliminated the catastrophic wear that terrified the warranty departments. This was the turning point. The roller lifter removed the penalty for using aggressive geometry. Suddenly you could have the secret trick, the fast opening and the high lift, without the reduced service life. The ultimate irony of this story lies in how it ended. As materials science improved and manufacturing technology advanced, the barriers that prevented Detroit from using Crane's ideas dissolved. The hate dissipated because the risk dissipated. By the late 20th century, the automotive landscape had completely inverted. The Big Three began facing stricter emissions regulations and higher fuel economy standards. To meet these new federal mandates while still making power, engines needed to be more efficient. They needed to breathe better. They needed exactly what Harvey Crane had been preaching since 1953. Modern engines from Ford, Chevrolet, and Dodge now universally utilize the very principles they once rejected. If you look at the camshaft specs of a modern LS engine or a Coyote V8, you will find asymmetrical lobe profiles designed to snap valves open for maximum efficiency. You will find split duration patterns to assist exhaust scavenging. And crucially, you will find hydraulic roller lifters as standard equipment. Innovation from the outside in. Harvey J. Crane Jr. did more than just sell automotive parts. He fundamentally altered the power dynamic between the car owner and the manufacturer. Before Crane, the engine was a sealed black box provided by Detroit, tuned to their specifications, their limitations, and their economic fears. The consumer was expected to accept the compromise of a symmetrical cam and a restrictive exhaust, because that is what the assembly line dictated. Crane shattered that acceptance. His legacy is not merely the invention of a specific lobe profile or a roller rocker arm. It is the transformation of the aftermarket from a collection of backyard hunches into a rigorous engineering discipline. By establishing the cam school and pioneering the use of computers in design, Crane legitimized the pursuit of speed. He took the intuition of the hot rodder, the feeling that an engine wanted to breathe deeper, and translated it into the hard science of degrees, lift, duration, and ramp velocity. He proved that a small shop in Florida could out-engineer the largest corporations on Earth simply by refusing to accept good enough as a design parameter. The secret trick of the asymmetrical lobe was never really a secret. It was a truth that Detroit was too risk-averse to admit. It demonstrated that reliability and performance were not mutually exclusive enemies. They were simply variables in a complex math problem that Detroit was initially too financially conservative to solve. Crane solved it. He proved that if you respect the physics, if you treat the valve train with the geometric precision it deserves, you can have the violence of a race car without the catastrophic failure of a grenade. Today, the spirit of Harvey Crane lives on in every garage where someone picks up a wrench to improve what a factory built. His story serves as a reminder that true innovation rarely comes from a boardroom committee meeting focused on quarterly profits. It comes from the fringes. It comes from the obsessive, the racer, and the machinist who looks at a finished product and sees only a starting point. Harvey Crane taught the world that the limits of an engine are not defined by the manufacturer who built it, but by the imagination of the engineer who rebuilds it.